Okay, so this is the equation we got in our last video. And we want to do some stuff with it. So I'm going to leave it at top for a minute. We're not going to use it at the very start. I'm going to use a different example, but we're going to talk about how we can do math with this equation. So let's say you run a factory that makes cars. And your cars, let's say we're going to make it really basic. We're going to talk about 3 parts. We need, to make our body of our car, we need one car chassis, or however it is. I say that, so that's like all the body parts, right? Then we're going to say we need to put some wheels on it. We're going to need 4 wheels. And we're going to make the doors separately, let's say. We put them on separately. We need 4 total doors. We're not going to worry about different doors being different. So we have one main body of the car, our car chassis. We have 4 wheels and 4 doors. Now, let's say my factory makes these 3 parts in 3 different places, and we want to put cars together. Let's say instead of having a nice, well-structured factory, I just kind of made some stuff. And let's say what I noticed is I have 12 chassis. However I say it. If I'm saying that badly, I apologize in advance. I don't know how to say the word. Let's say I had 12 wheels and 16 doors. And my question was, how many cars can each of these make? So first we can look at them by themselves. So let's say you had 12 chassis. Well, we know that each of these is equal to 1 car. This is how many we need to make a car. What you may notice is that equal sign, this looks a lot like what we did with conversion factors back in like meters and to kilometers. Same idea. 1 car chassis makes 1 car. That means if I want to do a conversion, I can say for every 1 chassis I have, that can be used to make 1 car. So in this case, we could get 12 cars from our 12 chassis if that was the only thing we had to worry about. Well, let's look at the others now. So we have 12 wheels. Can you see up here? Yeah. So we've got 12 wheels. I'm going to put a little. So we know that for every 4 wheels, we can make 1 car. Wheels cancel. So 12 divided by 4 means our 12 wheels could make 3 cars. Now we have 16 doors. So for every 4 doors, that can make 1 car. So our 16 doors can make 4 cars. So we have 12 cars, 3 cars, and 4 cars from our stuff. So this is how much each of those ingredients could be used for. Now, if this is exactly what I had, I clearly can't actually make all 3 of those, right? If I tried to make 12 cars, for example, then I would end up with 3 cars that are done, and then 9 cars that didn't have any wheels. I would also end up with 8 cars that had no doors. And I don't know about you, but I don't want to buy a car with no wheels or doors. That sounds like a bad idea. It probably wouldn't do a whole lot, right? So, in this case, I can only make 3 cars. Even though it looks like I should be able to make, if you just looked at the chassis, well, by golly, I can make 12 cars. What are you talking about? I don't have to worry about that wheel factory. I've got enough stuff. We can do 12. No, you have to talk to the other people. This same type of thing happens with chemical reactions as well. So, if we go up to our example up top, we can use numbers like our car examples, and we can say this. And I'm going to leave some of the car stuff up. We'll use that more later. So, for example, let's say I had, I'm going to write the numbers on top to make it easier to see. I'm going to use a different color. Let's say I had 4 moles of my C4H10. And I had, let's say, 13 moles of oxygen. Well, the question is, how many moles am I going to be able to make of stuff? How many times am I going to be able to do this reaction? So, if we make 13 moles of oxygen, that's what we have, and let's say I want to know how much carbon dioxide I'm going to make. That's what I'm going to look at. We know that every 13 moles of O2 makes 8 moles of CO2. I got that, remember, from the coefficients up front, like we talked about in the previous videos. Every 13 moles of oxygen that I react can make 8 moles of carbon dioxide. So the moles of O2 cancels, and I'll get that this 13 moles of oxygen can make 8 moles of CO2. Now, on the other hand, I have 4 moles of C4H10. And some people, when they think about numbers, might go, oh, 4 is less than 13. This is probably going to be what makes me run out first. But that's not true in this case. For every 2 moles of C4H10, I'm able to make 8 moles of CO2. So that means the moles of CH410 cancel. I do 4 times 8 and then divide it by 2. So I get 8 divided by 2 is 4. 4 times 4 is 16. I get 16 moles of CO2. What this means is that I'm going to run out of oxygen first. So the actual answer to this question is I make 8 moles of CO2. I can't make 16 moles of CO2 because that would require me to have more moles of oxygen first. Just like with our car example, we run out of something first. So there's some terms related to this. We have this term called limiting reactant. What limiting reactant means is it's going to be, in really simple English, is just what do you run out of? So to figure out what you run out of, you take each of your reactants and you convert it into one product that you can compare. If the problem doesn't ask for a specific one, you can pick whichever. So I picked CO2 here. You could have also picked water if you just want to know what you run out of first. So in this problem, my oxygen gives me 8 moles of CO2, but my C4H10 gives me 16 moles of CO2. That means I'm going to run out of the oxygen first because it makes less stuff, just like if it made less cars. So my limiting reactant in this problem is going to be O2 is my limiting reactant. Now, sometimes what you're interested in is what do you run out of, because it gives you an answer of what do you need to have more of. So in our car example, you want to know, do I run out of wheels first? Well, let's make the wheel factory make more wheels, or my car chassis factory go slower so it makes fewer car chassis because I don't want to just build up a warehouse full of car chassis and not have any wheels. So sometimes we want to know, what do you run out of? Because the thing you run out of is the thing you got to put more in if you want to make more stuff. It also tells you because sometimes you just have a limited amount. Like let's say in my car example, my factory stopped working and I'm just going to put together the last parts before I close it. Well, I want to know, well, I run out of wheels first, so I'm only going to make 3 cars, and that's it, and we're done. And that's okay, I just want to know that answer. So in chemical reaction land, this is a much more common example of you mix 2 things together, and well, you're going to run out of oxygen, that's fine, I just wanted to know, I'm only going to be able to get 8 moles of CO2, and I'm going to have some C4H10 left over. And that's fine. That's one of the possible answers to how we deal with this question. Now, I'd like to show you the other thing we want to know sometimes instead is how much are you going to make? So we're going to make 8 moles of CO2, and we're going to call this the theoretical yield, which is if everything works as expected, or if everything reacts as expected, how much would you get? So in the world of solving problems, this is fairly common. We're going to talk about theoretical yields. How much carbon dioxide would I make? My theoretical yield would be 8 moles of CO2. And I got that because I solved what's called a limiting reactant problem. Limiting reactant just means I have to look at everything I put in and see which thing runs out of first. Now, theoretical yield is what you're usually dealing with in chemistry homework problems like you solve in your textbook. Now, practically speaking, the theoretical yield is not what you necessarily always get, though. We know that reactions have limitations. For example, maybe they're not all that efficient. Maybe when I mix these things together, the combustion isn't perfect. And some of the oxygen doesn't react with this. So maybe I only get 7 moles of CO2 in reality. So when you literally do the experiment, so for a homework problem, I have to actually give you the actual yield. Like if you're in a lab and you mix these things together and you get an answer, the thing that actually happened is called the actual yield. So our actual yield is how much did you actually get? Now, this is something that when you're actually doing a lab, like a real lab and you're physically doing it, it's easier to tell the difference between theoretical and actual yield. In homework problems, it can feel weird because you didn't actually do it. I told you, oh, this person did this reaction, this is what they got. The thing that they actually had happen, though, is supposed to be your actual yield. Theoretical yield is what could they have done if everything went perfectly. Now, what I've shown you is the slightly more complex version, actually, in some ways. Let's show you that you can also sometimes have questions that make it a little easier to solve where you don't actually have to do this limiting reactant thing. So this is what happens when you're limited by, you've got set amounts of both materials. This isn't always a practical case though. Sometimes you're only limited by one thing. So let's look at what that would look like. And we'll do it with cars first, and then we'll do it with other stuff. So sometimes we don't want to worry about multiple ingredients. We just want to know. So for example, let's say instead of these being separate factory in the same place, they're separate factories. Let's say I run a door factory and I make car doors. I have no idea how realistic this is. I'm assuming it's not. I'm assuming no one runs a car door factory and ships them to another place, but who knows? I'm assuming it's hard to ship a car door efficiently. So let's assume I run a door factory though. We're gonna run a car door factory. And I produce 4,000 doors. Let's use a number that you can't... No, yeah, let's do that. That's fine. It's obvious, but... So I make 4,000 doors. I just want to know, how many cars can my doors make? Because other people are worried about the other questions. And they ask me, Dr. Leslie, how many cars can you outfit with doors? Well, if they ask me that question, then I just have to do this conversion. 4 doors makes 1 car. Not an R, a car. I need the C. So doors cancel. And 4,000 divided by 4, I can make 1,000 cars. So I can go back and tell the other people that run the bigger places, hey, I can make 1,000 cars. Sometimes the questions are like that. I don't care about wheels or car chassis. Nobody asked me that. So in that case, we just have to do a one-step conversion. So how does this work in chemistry? Well, because sometimes I know the examples can feel like, well, when would that come up? So let's take this example here. But instead of giving you both numbers, let's say this. I'm going to burn some fuel that's going to be C4H10. And I tell you that you have, let's work with a number we have to actually use a calculator for, 0.75 moles of C4H10. But instead of that looks like an O. But instead of telling you how much oxygen you have, I say, hey, you're going to do this outside. You have lots and lots of oxygen. It might as well be infinite. So we're going to tell you have, the word we're going to use in chemistry is excess. Your problem's going to say you have excess oxygen. Or it's just not going to ask about the oxygen at all. So if you're not given any information about it, what I'm told is, hey, how much CO2 do I make if I burn 0.75 moles of C4H10? So then we just have to do that first step. We don't have to worry about that converting over and comparing. So we have C4H10. And from there, every 2 moles of C4H10 makes 8 moles of CO2. So my problem's asking me how many moles of carbon dioxide can I get from my 0.75 moles. And I think my calculator has to boot up because, it needs an operating system. Yes, validating the operating system. I didn't think to do this ahead of time because I didn't realize I was going to need it. So if I do all this, I could have done that without a calculator. Oh well. So if we do this, we will make 3 moles of CO2. Now, as a side note, that's because 0.75 is 3/4. 3/4 of 8 is 6. 6 divided by 2 is 3. But you don't have to do that. You can put it in the calculator and say, okay. So we made 3 moles of CO2. Now, some problems are going to ask this a bit of a different way. Maybe I'm not going to know I had 0.75 moles. What if instead we ask this? If I burn 12.5 grams of C4H10 in the presence of excess oxygen, how much water is produced? So this is what it looks like as a question, what I would actually word it as. So if I burn 12.5 grams of C4H10 in the presence of excess oxygen, how much water is produced? So our chemical formulas are just for going from moles to moles. So we've got to start by doing that gram to mole conversion we talked about a couple chapters ago. So 12.5 grams of C4H10. Now what we know is we've got to find the molar mass. So that'll be, get that. I just multiplied instead of adding my masses together. 4 times 12. And then I just did something really ridiculous. How did I manage that? I put an 80, I've got 1,000 grams as my molar mass. And I know enough to know that is ridiculous. Oh, that's because I put 84 instead of 4 carbons. If you had 84 carbons, it'd be a much bigger molecule. So we get that for every 58.14 grams of C4H10, you get 1 mole of C4H10. Now in theory, you could do this and then write another problem to do the mole to mole conversion. But in this case, I like to just keep going in a big line. It makes it easier to organize. So for every 2 moles of C4H10, I can produce 10 moles of water. So this problem just asks how much water, but it doesn't give me a unit. So in this case, I can stop at moles because it doesn't tell me what to do. And unless it's a multiple choice question that lists them all in grams, I can stop at moles. However, if it said, what is the mass of water produced, I'd have to do one more step. You would do a mole to gram conversion as well. So in this case, because it doesn't tell me, I'm going to stop at moles. But if you had to, you could keep going and you could do this gram to mole conversion, but going back to water. So we have 12.5 grams divided by 58.14 is its molar mass. And multiplying by 10 and dividing by 2. I get that I'm going to be able to make, we had 3 sig figs at the start, so 3 sig figs in the answer, 1.07 moles of water. And if you need to, you could also find the mass of that by multiplying it by 18.02, which is the molar mass of water. So this is going to be a very common type of problem you have to do, where you have to take grams, convert them to moles, and convert them to moles of something else. You'll also notice that we have different types of moles in the same problem. This is why I have so heavily emphasized in so many problems, write out grams of what, moles of what, because it becomes very easy to look at your problem and get lost in your work and not realize, oh, this answer is moles of water, not moles of carbon dioxide. So to keep it straight, it's important we leave our labels on things. And you can check that the grams cancel and those moles cancel, and you're left with moles of water. So this is an example of what we're going to do with a lot of these problems. I'm going to do one that you now solve on your own. Well, you solve by pausing me, and then we go over it. So let's look at an example now. So our example is going to be, and we're going to purposely use some big numbers because it's okay for numbers to be big. I want you to determine the mass in grams of carbon dioxide produced when, see, I always, nice big number, 3.6 times 10 to the 5th grams of octane, C8H18, is burned in excess oxygen. It should say in the presence of excess oxygen, probably, but you get the idea. I just don't want to have to add a word in there. It makes it hard enough to read. And then we'll give you the chemical equation. 2 C8H18 liquids plus 25 oxygen gas molecules reacts to form 16 CO2 gas molecules plus 18 waters. Now, before I set you off to solve this problem, I want to point out that the first step should always be make sure your equation's balanced. I'm going to go ahead and tell you it's balanced. In retrospect, if I wrote this on a test and I wanted to speed you up, I would say using this balanced formula. But if it doesn't directly tell you it's balanced, you need to check that first. Because it might just be the unbalanced equation, and if you use an unbalanced equation, your ratios won't be right and you'll get the wrong answer. So I'm going to go ahead and tell you this one's balanced. You can skip that step for this one. So I want to know what's the mass in grams of carbon dioxide you can make from this 3.6 times 10 to the 5th grams of octane. So pause me and give it a try. Hopefully you've tried now. So we'll start with our starting information. We have 3.6 times 10 to the 5th grams of C8H18. Now, we need to first start by finding its molar mass and getting it into moles before we convert it to carbon dioxide. So we have 8 carbons and we have 18 hydrogens. That's going to give us a molar mass of 114.26 grams of octane, make 1 mole of C8H18, or octane. Now, we want to go to CO2. And we don't have to worry about doing a limiting reactant problem because they told us excess oxygens. We don't have to worry about running out of it. So, we know that for every 2 moles of octane, we're going to get, they said CO2. We'll get 16 moles of carbon dioxide. I got that 2 and 16 by looking at the coefficients in front of my numbers in my balanced chemical formula. Now we're going to finish off because it tells us to get to grams, so we can't stop at the other. Stop at moles, so 1 mole of CO2 has a mass of 44.01 grams of CO2. And we can check that our units work out. Our grams of C8H18 cancel. our moles of C8H18 cancel, and our moles of CO2 cancel, and we're left with grams of CO2, which is what they want. So we have 3.6 times 10 to the 5th. I'm going to multiply that by my stuff in my numerator first. Then I'm going to divide by my stuff in my denominator. Note that this is all communicative, so you can do it in different orders, and that's okay, as long as you make sure to keep it straight. So multiplication and division, you could divide by this first, then multiply by that, or you could multiply all the tops and divide by the bottom. Whatever you do, it's just important that you keep that consistent. So let's see, my answer reasonable? 1, 2, 3, 4, 5, 6. Yeah, my answer is reasonable, I think. Yep. So what we'll get is there's 2 sig figs at the start, so I'm only going to have 2 in my final answer. I would get 1.1 times 10, 1, 2, 3, 4, 5, 10 to the 6th grams of CO2. And again, it's a kind of big number because we started with a big number. So our C8H18 is able to burn into this much carbon dioxide. So this is the way you solve a problem like this. Another case where I think it's really about practicing these, because these conversions are going to be the core of everything going for the rest of the semester. We're just going to what we'll be changing up is we'll have some different ways. Maybe you won't always have grams. Maybe you'll have a volume. Later you'll have a pressure or an energy. But you're going to do a whole bunch of these conversions basically for the rest of the whole semester. So this is the core of the remaining of 1211, is different ways to figure out how much stuff do I have, how much stuff can I make? Because it's such a central question to chemistry. I want to know, what am I going to make when I mix some things together? That's why we're going to do so many of these, because they end up being such a relevant question to what we're doing.